Hi, everybody. This is Dr. Nigro with a bonus physics fundamental screencast. In my class currently in honors physics, we have been working on friction problems, and I found that my students get a little bit confused with these different types of problems and identifying where friction is and then how to calculate friction. So what I have here is a notes page with problems that my class worked on this week, and I've decided to do a screencast of it so that everybody can enjoy the awesome that is dealing with friction when we have systems, when we have angled forces, and when we have inclined plane problems. It's going to be a longer video because it's got all three problem types in one. Feel free to jump around, find what you need. Or if you would like to look at my standalone screencasts, you can find those on the Physics Fundamentals webpage. Okay, so we're going to start with what I consider the simplest of these three different problem types, which is our systems problem. In my class, we tend to deal with the block and hanger system when it comes to friction. So we're going to start by drawing our free body force diagrams. All right, first let's talk about the motion. All right, the hanger is going to drop, which means that the motion is going to be downward in terms of the hanger. All right, so the block is going to be sliding to its right across the bench top. All right, so we start with our free body force diagrams by looking at each individual piece and then the system as a whole. All right, so mass 1 is going to have a normal force supporting that block opposed by a gravitational force, and those should be equal but opposite. All right, then we're going to have a force due to tension on the right, and we're going to have a frictional force on the left. All right, you'll note that I drew my frictional force slightly shorter than my tension force. I know that the block is going to move to the right, so I know that that frictional force has got to be less than tension. All right, for my F net equations, I look at them in terms of parallel with the motion, which is in the direction of the motion. I'm going to have my tension force and then my frictional force. The way I've drawn my diagram, that tension force will be positive and that friction force will be negative, which means I need to hold on to that when I do any calculations. All right. For my perpendicular motion, that net force is going to be the normal force and then the gravitational force. All right. And again, the way I've drawn my free body force diagram, my normal force will be positive because it points up, and my my gravitational force will be negative. All right. So that is the block. All right. Now let's move on to the hanger. So this is mass 2. All right. Now there's only two forces working on my hanger. All right. And I, again, draw it so that it is in a straight line with mass 1. So that means that to the right is going to be that gravitational force, and then to the left is going to be the tension force. All right, let me make this a little bit longer because I know that that gravitational force is greater. Okay, now I only have one F net equation for this particular object because it only has one set of forces. All right, so that means that we're going to have a gravitational force versus the tension force. All right, and as I have drawn it, that gravitational force will be positive and the tension force will be negative. All right, because this is a system, once I draw my object free body diagrams, I need to look for action-reaction pairs, and I've got one in the form of the tension. So the tension on the mass 2 will be equal and opposite to the tension on mass 1. So those are going to cancel out, so I cross those out. And then what I'm left with is the system. All right, so my system is going to have two forces working on it. All right, I'm going to have the force due to gravity, and this is on mass 2, or the hanger. And then opposing that, I'm going to have a force due to friction that is acting on my block. All right, my F net equation for my system is going to be equal to the sum of these two forces. Friction. All right, for signs, my gravitational force is pointing to the right, so that's positive. Frictional force to the left, so that's negative. So I put a positive and a negative. Okay, so I'm going to be using those as I move into the rest of my problems. All right, one thing to keep in mind, just in general, all right, the absolute value of your frictional force is going to be equal to the coefficient of friction times the absolute value of the normal force. All right, this is going to be an equation that we're going to need before we can do any further calculations. All right, in addition, don't forget that normal force in this case is going to be equal and opposite to the gravitational force of that block. So we're going to need that formula as well because we're going to need to plug that in to our frictional formula. Okay, so let's move on to the problem. All right, a system includes a block that has a 1.25 kilogram mass and a hanging mass connected by a string over a pulley. The block has a coefficient of static friction of 0.55 and a coefficient of kinetic friction of 0.35. Using your free body force diagrams and F net equations above, answer the following. All right, so the first question is, what is the minimum hanging mass that's needed to put the system into motion? All right, so this idea of put the system into motion means it's not moving yet. All right, so that means we're dealing with static friction. All right, now this minimum hanging mass, we're trying to figure out, well, what is the mass of object 2? So that's going to be our unknown. So if I want to determine what the minimum mass needed is, what I'm really asking is, what is the minimum force due to gravity that's acting on that hanging mass that will be equal to the static friction? Because remember, the system will not move until your applied force is equal or greater than your static friction. And here, the force being applied is due to the dropping of that hanger. Okay, so with that in mind, I'm going to start substituting in for both sides of this equation. For the force due to gravity for mass 2, I'm going to plug in the value for mass 2 and then the value for gravity. All right, and then for friction, I'm going to need to use the static coefficient of friction and then the normal force, which we said above is equal to the force due to gravity on mass 1. So I'm going to say mass 1 times gravity. Okay, so if we look, gravity shows up on both sides, so we can cancel that, which is going to help a little bit. And we end up with mass 2 is equal to my static friction coefficient times mass 1. All right, so mass 2 is going to be equal to 0.55 times 1.25 kilograms. So mass 2 is going to be 0.688 kilograms. So the minimum mass that will put the system into motion will be 0.688. If I have a mass less than that, the system will not move because it will not have provided enough applied force to overcome the static friction. All right, let's look down here at part 2. All right, here it asks how far has the block moved in 0.8 seconds after we release the block, the hanger rather. Assume it starts from rest. All right, I always like to start my problems when we're asked questions about distance or velocity or time by putting together my variable list. All right, so here are my variables. Now we're going to start from rest, so that means this is 0. I don't have a velocity. I don't have an acceleration. I do have time, so 0.8 seconds, and I'm asked to find that change in position. All right, well, to find that, I really need to find that acceleration. So my first step will be to find the acceleration, and then I'm going to use that and my other variables to find that position. All right, so how am I going to find that acceleration? Well, I'm going to need to find the net force, and then I can use Newton's second law, mass times acceleration, to find that acceleration. All right, so I'm going to go back up to my free body force diagrams, and I'm going to look at what the F net equation is for my system. All right, and I see that it's equal to the gravity acting on mass 2 plus the frictional force that's acting on the block. All right, so F net is going to be equal to the mass of block 2 times gravity plus negative coefficient of kinetic friction times the mass of block 1 times gravity. All right, because remember, it's the coefficient of friction times the normal force, and we've defined the normal force as being equal to Fg of the block for this system. All right, now that negative sign, you may ask yourself, why did I do that? Well, if you go back up and look at our free body force diagrams, you can see that that frictional force should be negative. So we need to make it negative, because remember, the formula for friction is an absolute value. So all we get out of that formula is the magnitude, and it's up to us to fix the sign. All right, so F net is going to be equal to the mass of 2 times gravity, so that's going to be 6.88 newtons, plus negative kinetic coefficient of friction times mass times gravity. All right, so we're going to end up with 0.35 for my coefficient, because I need the kinetic one, sorry about that. And then we get 12.5 newtons for that Fg for mass 1. All right, put all that in our calculator, and we're going to find that the F net for the system is equal to 2.5 newtons. All right, now that 2.5 newtons is also equal to the mass of the system and the acceleration of the system. All right, the mass of the system, remember, is just the sum of the masses. So the acceleration is going to be equal to 2.5 newtons divided by the mass of the system, which is 0.688 plus 1.25 kilograms. All right, and I find that the acceleration here is going to be equal to around 1.3 meters per second squared. Okay, but we're not done, because the problem wants to know, well, what is the change in position? All right, so I'm going to use my change in position formula equals the initial velocity times time plus 1/2 acceleration times time squared. All right, this initial velocity is 0, so this piece goes away. So that change in position is equal to 1/2 of 1.3 meters per second squared times 0.8 seconds squared. And I find that the block will have moved about 0.42 meters during that 0.8 seconds after I release the hanger. Okay? All right, the last question here, this is tension. What is the tension in the string? All right, so you have two choices. You can go back up and look at your free body force diagrams. All right, we have tension in this formula, where we look at it from the perspective of the block, or mass 1, and then we have tension in this formula, where we look at it from the perspective of a hanging mass. You can choose either. I tend to go with the hanging mass here, because that's a pretty easy calculation, whereas if I have to use the block, I got to figure out friction again. So I'm going to say that the F net that's working on mass 2 is going to be equal to the gravitational force on mass 2 plus that force due to tension. All right, now the net force is going to be equal to the mass of 2 times the acceleration of the system. All right, I know that Fg for mass 2 is 6.88 newtons, and my unknown is going to be that tension force. All right, now the reason we use the acceleration of the system, remember, everything's connected. So if we say the system's moving at 1.3 meters per second squared, that means the block's moving at that acceleration and the hanger. They all go together. All right, so we end up with 0.688 kilograms times that acceleration value is equal to 6.88 newtons. Oh, whoops. I'm sorry. Hold on. Not that. I know what the acceleration is. I just found it. Times 1.3 meters per second squared. And that's equal to 6.88 newtons plus the force due to tension. All right, so once I do this multiplication and then I subtract 6.88 to the other side, I find that the force due to tension is equal to -6 newtons. All right, the negative sign comes out in the math, and if I look back up at my free body force diagram, it had a negative sign, so I'm good to go. Okay, so that's just an example. You have to be able to draw the free body force diagram, so please make sure you practice that. All right, let's move on to our second problem type. All right, this time we're looking at an object that is being pushed across the floor or pulled across the floor with an angled applied force. All right, so this is my applied force that's being pushed down. All right, and then this is my applied force where we're being pulled upward. All right, maybe actually instead of the word down here, I'm going to say downward. All right. The reason I don't want you to get confused with somebody pushing a block through the floor or on the other side, someone pulling a block up off the floor. It's just the angle is downward or the angle is upward. The block is still moving horizontally. Okay. Now, because because the applied force is angled, then we have to split it into its two components. All right. So we start by drawing this piece and then add tip to tail this piece. Our angle is here, which means this is the applied force X component, and then this is the applied force Y component, okay? Now, when we draw a free body force diagram, we need to include those two components. We should not show an angled force in our free body force diagram. We should instead split it into its components and then draw the free body force diagram, all right? So here's my toy box. All right, if I look vertically, all right, I see that I'm going to have a gravitational force pointing down, all right? But in addition, based on my applied force, there's going to be a portion, the Y component, that also points down. Now, the box is not floating or sinking, so opposing those two forces, equal and opposite, is just the normal force. All right, so you can see that in this case, that normal force is greater than the gravitational force. So the surface is applying or is providing more support than it would if we were either pulling at an angle of 0 degrees or upward. All right. Now, let's talk about our vertical forces. All right. So let's say we're pulling, the motion is going to be in this direction. All right. So that means I've got my applied X component. Now that is your applied force. That's what's causing the motion. And then opposing that on the other side is our frictional force. Okay. All right. So again, if we look at it in terms of F net, and we talk about the perpendicular portion, we're going to have our normal force plus our gravitational force plus the applied force in the Y direction. All right. If we look at our diagram, these three together are equal and opposite. So in other words, our normal force is equal to the sum of our gravitational force plus the Y component of that applied force. This is really important because that's going to be important when we calculate our friction value. All right, for signs, remember the normal force points up, so it's positive. The gravitational force and the Y component both point down, so they are negative. And because we're not moving in this direction, the net force must have been 0. Okay? Now let's look parallel. So our net force parallel is going to be equal to our frictional force plus the X component of our applied force. Okay, so again, we talk about signs. Our frictional force is to the left, so it's negative. Our applied force is to the right, so it's positive. I don't really know what's going on with the net force. Kind of depends. If friction is greater than that applied force, then we're going to be slowing down. If friction is less, then we might be speeding up. And if the two turn out to be equal, then we're moving at constant velocity. All right. Now, when we work these problems, just in general, remember, all right, the applied X component is equal to our applied force times the cosine of that angle, and the Y component is equal to the applied force times the sine of that angle. All right, we need to remember those because we're going to need them if we're going to calculate our frictional forces and then our applied forces. All right, specifically, I know that that frictional force is going to be equal to my coefficient. It depends on whether it's moving or not. All right, times the normal force. And we just said above that that normal force is actually equal to Fg plus the applied force Y component. All right, so we're going to be mixing and matching these, and it's going to look a little messy, but we can do it. All right, if we think about it, because this normal force is so much bigger than gravity, all right, that means that that normal force value will be bigger. The frictional force is going to be higher than if we were just pulling it in a straight line instead of pushing down on the object. All right, let's move over to our other situation. All right, this time we're pulling upward. All right, so we're again going to split it into our components. All right, let me move this FA. so that it's up here. There we go. Here's our angle again. All right, we've got our y component and we've got our x component of that applied force. All right, so we come down to do our free body force diagram again. Again, starting with our vertical forces. Now this time, if you look, that y component is pointing upward. So the applied force y component is now going to work with the normal force. And together, they will be equal and opposite to the gravitational force. So these two add up to this one, okay? Horizontally, I still have the x component of my applied force and it's working against my frictional force, okay? For the F net equations, so the F net perpendicular is going to be equal to the normal force plus the y component of the applied force plus that gravitational force. All right, for sines, this time the normal force is still positive, but the y component has switched from negative to positive. All right, and then we're going to have an FG value that will be negative. All right, before we said Fn is equal to Fg plus Fa y component. But now if we look, Fg is equal to the normal force plus the y component. So if I rearrange this formula and solve it for the normal force, I find that the gravitational force minus that y component is going to give me my normal force. All right, so that's a little different than what we saw in our other situation. All right, if we switch over to the parallel net force equation, it's going to look exactly the same. The frictional force and the x component of my applied force. All right. For sines, same idea. Negative for friction, positive for that applied force. Don't really know for the net force until we get some problems going. All right. Don't forget that frictional force is going to be equal to the coefficient times that normal force. And we're going to need to plug in this equation for that normal force. All right, so again, you can see why the angle forces make things a little bit more complicated, but it's not that bad as long as you write out your F net equations for both directions, and then you can find the normal force so you can find the friction. All right, so let's try. Dr. Nigro is snowblowing her driveway at home. She pushes her blower, which has a mass of 178 kilograms, with a force at 40 degrees below the horizontal. The tires of her blower have a friction coefficients of 0.35 and 0.28 with the pavement. What is the minimum force needed to move the blower? All right, so that minimum force means that we are looking for the applied force that I will be applying at this angle of 40 degrees below the horizontal. So we're not looking for a component, we're looking for the actual force itself. All right, and it says to move the snowblower. So that means I'm trying to figure out what FAX is, because if that is equal to the static frictional force, then the blower is going to move. All right, now why is it FAX instead of FA? Because FAX is the portion of the applied force that's directly opposite friction. All right, so you need to pay attention to your drawings. There's a reason we have you draw these things. And if you try to do it without the drawing, then you're going to make some mistakes. All right, so I'm going to set these two equal to each other. All right, so FAX equals the static friction. All right, so for FAX, the formula is pretty straightforward. It's the applied force times the cosine of the angle. For my static friction, I'm going to need the static friction coefficient and the normal force. All right, now I could do some plugging in, but in class, I found that that was very confusing for my students. So instead, what I'm going to do is go over to the side, all right, and I'm going to solve for the normal force. Now up above, I found that the normal force was equal and opposite to the sum of the gravitational force and the y component of the applied force. So Fg plus the y component of that applied force will give me the value for Fn, and then I can plug that in over on the left. So let's do that. So the normal force, so the gravitational force is 1,780 newtons, because I'm using 10. All right, Fay is equal to the applied force times the sine of the angle. All right, now the angle is given, so instead of putting in that, I'm going to put in 40. All right. So if I finish this up, I have 1,780 newtons plus the applied force times the sine of 40. Hold on, let me put that in my calculator, which is 0.64. So I'm going to take this and I'm going to plug it in to Fn over here. All right. So the applied force times the cosine of 40. So the cosine of 40 is equal to 0.77. That's going to be equal to mu, which for static is 0.35 times 1780 newtons plus 0.64 FA. All right, so I'm going to need to distribute this to these two guys, and I get an applied force of 0.77. I get the applied force times 0.77, and that's going to be equal to 623 for 0.35 times 1,780. And then here, I'm going to get 0.35 times 0.64, 0.224 times FA. So I need to isolate FA. So I'm going to subtract that 0.224 to both sides. So when I do that, I get the applied force times 0.546 will be equal to 623 newtons. Oh, whoops, hold on. I messed something up. 0.77 minus 0.225. Oh, no, that's right. Okay, so I'm going to divide both sides by the 0.4546, and I find that the applied force here should be in the ballpark of 1,151 newtons. Okay, so that is the minimum force that I can apply at this angle and make my snowblower go. All right. All right, so let's look at our next problem. All right, if I use a force of 1,500 newtons, how far will I move in 10 seconds? Again, assume the blower starts from rest, okay? So again, asked about distance, so I'm gonna set up a variable list, initial velocity, final velocity, acceleration, time, change in position. This time I've been given an applied force, so I'm gonna put that in there too. So we start from rest, it'll be 0. Don't know the final velocity, don't know the acceleration. I have 10 seconds to move, and I'm asked to find the change of position and given an applied force of 1,500 newtons. All right, so similar to our problem above, I'm going to have to go find my acceleration first, and then I can find that change in position. All right, now the problem tells us the applied force. It says that I'm pushing it with 1,500 newtons. So that means that I'm applying enough force that it's just going to go. I don't need to worry about overcoming static friction because I'm applying more than I would need to overcome that static friction. All right, so when I set up my F net equations, all right, I'm still going to have my frictional force, but it's going to be kinetic friction, and I'll be dealing with the applied force in the x direction. Okay, all right, I know that my force due to friction, just come here, buddy. I know that this force due to friction kinetic, all right, I'm going to substitute in. All right, this is going to be negative, right? Because up in my free body force diagram, I said the friction was pointing in the negative direction. And that'll be my kinetic coefficient times my normal force. All right, and then that's going to be plus that applied force times the cosine of my angle. All right, so let's start plugging in. So F net is going to be equal to negative 0.28 this time. All right, now the normal force, as we saw before, is equal to the gravitational force times the y component of the applied force. So you know what? Maybe I'll just do that down here. Fn, that's going to be equal to 1,780 newtons plus 1,500 newtons times the sine of 40 degrees. All right, so if I plug that in and then add the two together, I find that my force value, what did I do wrong here? Is 27, where'd it go? There it is, sorry, 44 newtons. All right, so I'm going to multiply that, 2744 newtons plus 1500 times the sine of 40, 964 newtons. All right, so when I distribute that 0.28, well, it's not really distributing. When I say 0.28 times 2744, all right, I get a negative 768 newtons plus 964. What am I? My answers seem off from what I got before. All right, let me try that again. The applied force, so the cosine of 40 times 1500. Oh, that's what I did wrong. Sorry about that. I knew something was wrong. I hit the sine button instead. So this number should be 1149 newtons. Sorry about that. All right, which means my net force is going to be 381 newtons. All right, now we know that is also equal to the mass times the acceleration. All right, so that means my acceleration is going to be equal to 381 newtons divided by 178 kilograms. All right, so I'm going to have an acceleration of 2.14 meters per second squared. All right, so that's going to be used along with my other variables to find my change in position. All right, so again, I'm going to use my v initial times time plus 1/2 at squared, initial velocity 0. So that change in position is 1/2 of 2.14 meters per second squared times 10 seconds squared. And when I plug that in, I find that I have moved 105 meters during that 10 seconds due to the force that I'm applying to the snowblower. Okay? All right, let's move to the last problem. All right, these are also fun. All right, I love inclined planes because I like drawing triangles. So this satisfies a need in me. All right, for this first one, we're looking at a box that moves up the ramp. All right, so the motion is going to be in this direction. All right, if we start by drawing the forces in play, we're going to have a downward force due to gravity. That's always straight down. All right, then opposing that, perpendicular to the surface is going to be the normal force. Now, those two forces are not directly opposing each other, so we're going to need to split that gravitational force into its x and y components. All right, so you can see I have a gravitational y component here and a gravitational x component here. All right, now this inclined plane has an angle of 25 degrees. That angle goes right here, whoops, in my new triangle. Okay, so for both of these, we're going to use sine and cosine. If I'm trying to find the x component of that gravitational force, I'm going to need to know Fg, and then I'm going to multiply it by the sine of the angle. And that's a little different than what we've been doing before. All right, before the x component was always the cosine. Now, because of the way the triangle is facing and where the angle is, it's going to be the sine. If we need the y component, we're going to need, again, the gravitational part, and then we'll take the cosine of the angle. So these two are going to hold for both situations. Okay? All right, now let's talk about our free body force diagram. All right, so here's my toys. All right, I'm again going to have vertical and horizontal forces. So my vertical force upward is just going to be that normal force. All right, and then opposing that is not Fg, but instead it's the y component of Fg. And it's important that you make that distinction because Fg and the y component are two different numbers. These two are going to be equal and opposite to one another. All right, horizontally, because the box is moving up, all right, that means that friction is going to be pointing in the opposite direction of the motion, so to the left. All right, but in addition, according to our triangle that we drew under our toy box, there is also a component of gravity that's working with the friction. All right, so it's against the motion, both of those forces. All right, for our F-net equations, if we start with our perpendicular forces, we're going to have our normal force, and then we're going to have our gravitational force y component. All right, for sines, normal force is up, gravitational force is down, and because the box is not moving vertically off of the ramp, my F-net is going to be 0. All right, and that's handy because that means I can say that the normal force must be equal to that gravitational force, all right, which we're going to use when we start doing some calculations. So you need to remember this piece as well. All right, now we're going to move on to our net F-net equation for the parallel forces. In this case, we've got the applied force, the gravitational X component, and then our frictional force. Right? Both of these point to the left, so they have the same sign. They're both negative, which means the net force overall is going to be negative outside of any additional applied forces. Now, we could have somebody pushing the box too, all right, and then we would have to add in that force as well. But you just need to read the problem to decide if that's the case. All right, don't forget the force due to friction is equal to the coefficient times that normal force. And we've indicated that that normal force is equal to FG y component, okay? All right, now if we move to the other situation where we're going to move down the ramp, all right, that means the motion is in this direction. All right, a lot of this is going to look the same, all right? We're still going to have our downward gravitational force. We're still going to have our perpendicular normal force. We're still going to need to split this into its 2 bits, where we have a y component of gravity and an x component of gravity, and our angle is going to be here. All right, the difference was when we get to our free body force diagram. All right, so we've got our toys. All right, we're going to start with our vertical forces. They're going to look exactly the same. Normal force up, gravitational y component down, equal and opposite to one another. All right, the triangle tells me that I still have the x component of my gravitational force pointed to the left. So I'm going to leave that. But because the motion is also to the left, friction this time has to be to the right. Because remember, friction opposes motion. And that's it. If the motion is going in one way, friction's going in the other. Okay, so let's write our F-net equations. So F-net perpendicular is going to be equal to the normal force plus the y component of your gravitational force. For sines, same thing as before, positive for the normal force, negative for that gravitational force, and we're going to have a 0 for our value for F net. So once again, that normal force must be equal to that gravitational y component. All right, we then move on to our net force for the parallel motion, and we're going to have our x component of gravity plus that frictional force. The difference is while the x component remains negative, this time the frictional force is going to be positive. So you need to be careful when you're putting these numbers into your problems because you got to make these positive or negative. The math may not do that for you. All right, so once again, that frictional force is equal to the coefficient of friction times the normal force. And we know that the normal force is also equal to that y component. All right, for either of these, just keep in mind, you could have an applied force present as well. You just need to add that in to the correct spot. That applied force is going to be part of the parallel motion, okay? All right, so let's work this problem. All right, Dr. Nigro leaves a large box of 150 kilograms at the top of a ramp with an incline angle of 25 degrees. The friction coefficients between the box and the ramp are 0.58 and 0.31 for static and kinetic. All right, so does the box start sliding down the ramp? So all the box is doing is sitting there, and I'm going to let it go, and I'm going to see if it's going to slide. All right, so what that means is similar to what we did on some of our earlier problems. I don't want to do red. Hold on. Let's do orange. All right. I need to decide, all right, if the force due to gravity in the x component is greater than or equal to the force due to friction static, then box will slide. All right, so I'm going to need to decide that first. All right, so I'm going to do just what I've done on my other problems. I'm going to set those two things equal to each other. All right, so the friction static value. All right, now I know that the FG component is the force due to gravity times the, hold on just a second. All right, nope, not cosine, sorry. Sine of your angle, right? And that's going to be equal to the static coefficient of friction times that normal force. All right, well, remember up above, we said that normal force is equal to the y component of gravity. All right, so if I rewrite these, I'm going to have mass times gravity for Fg times the sine of my angle equal to that coefficient times mass times gravity times the cosine of that angle. And I don't know if you noticed, but mass is on both sides and so is gravity. So I can cancel both of those out. All right, and I can solve and see if the two sides are equal to each other. All right, so the sine of 25 degrees equal to 0.58 times the cosine of 25 degrees. So when I plug these into my calculator, I find the sine of 25 degrees is 0.423, and the cosine of 25 degrees is going to be times 0.58, 0.523. All right, so they're not equal. And as a matter of fact, the force due to gravity for the x component is less than that frictional static value. So your box will not move. It's just going to sit there right there on that incline and not move. You'll have to give it a push if you want it to go. All right, and that's what the next problem is about. What is the minimum applied force needed to get the box to start moving? All right, so let's think about our F net equation. So it's going to be equal to that gravitational force in the x direction plus our frictional force. This time it's going to be kinetic. Oh no, not kinetic, because we're still overcoming the static, right? Because it isn't moving yet. All right, so let me fix that. Static plus some sort of applied force. That's the push that I need to give it. All right, so if this is going to work, the net force is going to be equal to 0 because it will just be getting ready to start moving. All right, I know sign-wise, I'm going to have a negative sign for FGX. I'm going to have a positive sign for the friction because it's moving down the ramp. And I'm going to give it a push from the top to the bottom, so that means my applied force needs to be negative as well. All right, so let's calculate. All right, we'll start with F net being 0. Oops. And that's going to be equal to FGX. All right, so I already said it's negative, and it's going to be the mass times gravity times the sine of the angle. All right, so my box is 150 kilograms, so 1,500 newtons times the sine of 25 degrees plus the static coefficient of 0.58 times Fg, the y component, because remember that's what equals our normal force. All right, so 1,500 newtons times this, not the sine, sorry, cosine of my angle, plus an unknown negative applied force. We don't know what it is. As a matter of fact, we don't necessarily need to put that negative in there. The math is going to do it for us. So just to avoid confusion, we'll keep it out. Okay, so let's calculate. All right, so I'm going to get a negative 634 newtons for that gravitational piece, a 788 newtons for my frictional piece, and then my unknown applied force. All right, so if I add these two values together, I'm going to find that I have 154.5 newtons plus my applied force. I moved the 154.5 to the other side, so my applied force will be equal to negative 154.5 newtons. All right, so I need to add a push that is at least 154.5 newtons. All right, if I push it at less than that, it's still not going to be enough to get over that static friction. If I push it greater than that, then I'm in business. It'll be moving. Okay? All right, so I hope this helps. If you have any additional questions, please ask. And as I said in class, you got to practice.